Monitoring. All right, well, we'll go ahead and get started. Great to see everybody here. We're a little bit fit nicely into this room. Is that a good way to put it? Yeah, but great to see a full house. And here we are for the Wednesday noon WIGIS forum time for an event co-sponsored by School of Computing. So it's great to have that, and it's super great to have Dr. Shaowen Wang here with us today. We've been planning this for quite some time, and weather tried to sabotage some of our plans, but we worked through it on his first visit to Wyoming ever, I think, not just the first visit to Laramie, but first visit to Wyoming ever. So it's my pleasure to be able to introduce him to y'all today. So just a little bit about Dr. Wang. He's professor and head of the Department of Geography and Geographic Information Science at the University of Illinois, Urbana-Champaign, where he's also a faculty fellow with the Office of the Vice Chancellor for Research and Innovation. At Illinois, he served as the Associate Director of the National Center for Supercomputing Applications for CyberGIS from 2010 to 2017. He was also the founding director of the CyberGIS Center for Advanced Digital and Spatial Studies at UIUC beginning in 2013. He hasn't slowed down. Currently, he serves as the PI and director of the National Science Foundation's Institute for Geospatial Understanding through an Integrative Discovery Environment, also known as iGuide to some of us that follow this. There's many acknowledgments of his contributions to the Academy. I'll add that he's a fellow of the American Association for the Advancement of Science. He's also a fellow of the American Association of Geographers. And I was at an event last week in Denver where he was acknowledged for honors as the 2022 AAG Distinguished Scholarship. With that, I'll say again, we're so happy that you're here and looking forward to your remarks. And everyone, please join me in welcoming Dr. Wang.
Well, thanks very much, Jeff. We solved the problem together, after all. But it's such a pleasure to be here and got to see longtime friends and colleagues such as Gabriel and meet new friends and colleagues and learn about all the amazing work you're doing here. So thank you again for having me and this opportunity to speak with you about geospatial discovery and innovation in the era of artificial intelligence and CyberGIS. I'll dive into this if I can. Are we good on the Zoom side?
Yeah.
All right, awesome. So a little bit motivation. The world is facing many challenges, and these challenges are not owned by separate disciplines or fields. And these problems sometimes referred to as wicked problems, such as sustainable development goals, oftentimes referred to, and just a few examples here as we see the donut, but in the middle, clearly we recognize the opportunities of this convergence, because even from the scientific practice, for instance, some of us does modeling simulation work, some of us does data analytics work, some of us goes to field to do our observations. But overall, we see the need of converging these different scientific paradigms. And the geospatial data and computing and software clearly is situated as a unique approach, driving this all together. And of course, meeting the requirements from a variety of complex problems the world is facing. So what is the geospatial discovery and innovation? Let me break down this terminology. Essentially, it's the intersection between geography and spatial science. And from geography side, we look at human, bio, physical, human environment interactions. And from the spatial science side, we have photogrammetry, remote sensing, spatial analysis, cartography, and so on and so forth, right? And of course, there are also bridging disciplines, such as GIS in the middle. So what is GIS? Maybe I'm preaching the choir. So it's a very overloaded term. Initially was referred to as geographic information systems. So it's a kind of technology, right? And I actually used the technology to get here. You might wonder. So, but it became also a branch of information science, referred to as geographic information science. And it's a major piece of our societal fabric. So it's a geographic information society. And it's a services, right? I used the navigation service to get here, but it's a synthesis approach. It's combining diverse sources of data and information to derive knowledge and insights. So this combining power is synthesis. And we also need to look very carefully at why spatial is special and requires treatment other than generic information, not having location components. And it's a big industry, billion-dollar industry. And the most recent momentum coming from this industry and this field is associated with geospatial big data. And speaking of big data, I think most of us, if not all, here are familiar with the popular V notions, right? Tons of data volume and lots of different kinds of data variety and veracity and validity and so on and so forth. I think if you look at geospatial data, it has all these elements of V. But if we look at the critical attributes of geospatial big data, these are the characteristics. You know, it's incredibly diverse, right? And heterogeneous, and it's dynamic. Each one of us actually in the room, I would argue, is a producer of geospatial data. As we carry our devices, move around, you probably don't pay much attention to whether you agree to make your location information available to some of the apps. You ignore them, you are, okay? You're opt-in, right? So we're producers of geospatial data, and it's massive. You think about how many of us are currently interacting with the location technologies, and it's global, right? Large scale and with a fine granularity at an individual level like us, and it requires distributed access, and oftentimes associated with privacy and protection of identities, and then confidentiality. So it's thorny data compared to a lot of natural science data. You don't have to worry about this distributed access. So I would argue geospatial big data is one kind of big data, most exciting, but also very challenging to work with. So here's a quick example. This was a few maps created by a grad student. His name is Dan Dongyin. And I think Professor Hugh would know how this map could be made. So it's based on Twitter. Anyone could tell me where this is? All right, you got it. Not a surprise, given that you grew up in Champaign. This is only a week of tweets that represent Chicago's built environment pretty well with the location signatures of Twitter data you could use through open APIs, right? This is unheard of. If you would tell me around the time I did my grad school, at the beginning of this century, I would laugh at you, say, oh, you could do this with geospatial data production simply from open source data with noise and with uncertainty associated with the process of generating such data. But here we go. We have this possibility and capability. And on the other hand, that's the rise of computing power and your creation of School of Computing, just a fantastic strategic move, right? And this is a machine going to be live later this year. It's called Aurora. It's funded by the Department of Energy. It's going to be hosted by the Argonne National Lab. It's going to have about a couple of quintillion calculations per second. Okay, so how fast is that? All right, so this is a bigger question for our School of Computing folks. Yeah, 18 zeros. That's a lot for 1 second to get this speed. But I think if the trend of the computing power increasing is holding, in about a dozen years, this computing speed and power will be with me in my pocket. So this is not too far away in our horizon. So we need to think ahead what this means for a lot of problems we're trying to solve, because it's coming very quickly. to be widely available to us. Although initially always this high-end computing approach is available for a lot of tough scientific problems, but after a while, it will become widely available for us. So CyberGIS essentially is to harness this big data movement and take advantage of big compute like Aurora and address big problems I was motivated by through collaborations. It's a team science approach. So it's a cyber-based GIS. And this was first appeared in the literature. I made the argument at that time. It was not a popular view yet, because you might recall, if you are GIS expert around 2010-ish, that was still personal computing dominated GIS approaches. But I started imagining at that time, GIS is really departing from that paradigm, become this integration synthesis-based through harnessing high-performance computing, big data to knowledge transformation, high-fidelity interactive visual analytics, and collaborative problem solving, right? GIS, even today, the mainstream approach is still very much individual user-based. It's not enabling collaborative problem solving that well. But I think we're making progress toward collaborative problem solving. So around that time, 2010, this is a special feature. Dar Wright, who's currently now the S3 chief scientist, and I organized this to just scratch the surface to show the exciting frontiers in science that could be enabled by geospatial cyber infrastructure and CyberGIS. And fast forward, I want to organize my talk as follows, after just a quick introduction to the background. I'll start with some examples, which I argue are going to be only more data and computation intensive. And then I'll go down from the top to give you the motivation and also reasons why we need to further develop geospatial data science and the CyberGIS. And there's also this enabling advances of computing from bottom up. I'll end with the possibilities of CyberGIS going into the future. So let's start with a few examples. I know this part of the country is incredibly rich in terms of the types of landscapes, and the natural environment is super beautiful and attractive. If I give you a couple of remote sensing imagery for any parts of your land, you would wonder, wow, is this wetland or forest, mountain or snow? It's hard to tell, right? If you get LiDAR for the same area, you could have a better clue, because it gives you that vertical representation of the same landscape. And on the right side here, you see that hollow part that could be trees or canopies covering maybe river channels. So that's the general idea. Of course, I'm looking at Illinois, that's where I'm from. The southern part of Illinois has this very diverse land use types, from urban to rural to agricultural to vegetation, like forests. So the work we did was to combine conventional remote sensing imagery, two-dimensional representation with LiDAR, the three-dimensional point cloud, which you could manipulate, and to give you the labels for training of your neural network model, like this one. But the mainstream neural network models, they are not very much tailored to geospatial data and the geospatial representations. So the work we had to do is really to figure out the representations from the geospatial side for combining the LiDAR 3D with the 2D remote sensing imagery, tailor that to the pipe of such a convolutional neural network. And I think there's going to be more work needed in this space. How do we frame neural net to be more geospatial friendly? And how do we have such neural network models not just fit into single modality of learning, but multiple types of geospatial data sources? And how do we even go further, create foundational models, like the language models you experienced the hype, ChatGPT, but in the geospatial space, we could establish similar foundational models. So these are related, I think, challenges and opportunities. But for this particular study we conducted, you could easily tell this is a conventional benchmarks. You got false classifications for land use, red color, this is built environment kind of features, but now got properly classified right using our neural network model. These are water body related features. Just quickly highlight a few examples there. So over the board, you could achieve much higher level of performance for getting the features classified right. Now, the idea was very intuitive, right? It's simply combination of multi-sources of geospatial data, both three-dimensional and two-dimensional. But I want to also point out, even for a model like this, focus on a single county in Illinois, you actually have to do a lot to keep computers busy. And we conduct this work using a small scale high performance computer, which I'll tell you about later. It's called the Roger. We actually kept that machine busy for nearly a week for training the model to get the model ready for the classification task. So now that's just one county. For those of you who are familiar with the national land cover classification, maps, the multi-agency effort, we want to do this for the entire country, right? And there's a recent opportunity to enable us to do this at much finer scale, which is this USGS 3DAP program, three-dimensional elevation program. It's sort of the go-to place to get your topographic data. And now we're pretty close to have the lower 48 states covered through LiDAR data acquisition. It's a federal agency, USGS, and local partner industry partnership. It's amazing. So the data we get from LiDAR is vertically within 10 centimeter accuracy, and horizontally you got at least a couple of points per square meters. So it's a much higher resolution than, for instance, the current generation national topographic data, which is NED. And the total NED data set, for those of you who are working with that data before, it's only about ½ terabyte, right, raw data. But for this 3DAP, single scan raw data, multiple petabytes. So you would not even want to try to download that to your personal computer, would you? No, okay. Let alone you want to subset the data to feed into the model I was talking about. So how do we do this? Clearly the aspirations for the entire country. Clearly the model could work. How do we scale this up? Well, my simple argument is we could keep Aurora busy as well, even just for the single problem. That's what the geospatial requirements and solving this real world problem could get us as both challenges and opportunities. So I was giving you a natural environment example, given how attractive here Wyoming is from the nature side. But it's also about the social environments and dynamics. Here are a couple of examples. On the left is to represent social unrest across the globe. There's a database maintained at the University of Illinois, the Klein Center for Democracy there. It has location components and depicting the dynamics across different areas of the globe. If some social unrest is happening, how could you, for instance, anticipate what might be some consequences? Actually, there's some social unrest in this country as well. And you probably know the reasons. And on the right side, this is actually Twitter-derived human mobility. You got millions, hundreds of millions of Twitter users like myself. I tweeted at Champaign, and I came here, and I tweeted again, and I formed a trajectory from Champaign to here, right? And then collectively, you have massive population. That's the aggregated view of human mobility. So you have this space, time, and human dimensions all combined together. And if you want to conduct analytics in this fashion, in this integrated fashion, whatever GIS tools today you have, you could purchase. You're not able to do this. It's a new data model because the conventional GIS data model is largely focused on rigid spatial measurements, boundaries, polygons, rivers, tables, right? Have all these coordinates. And this is intersecting not only that, but with the time. and also dynamics of human entities. So we need new geospatial representations, build on top of that new analytics to work. That's one of the problems CyberGIS is trying to tackle. And we cannot tackle such problems without collaborations, without team science. So this example shows for the production of biomass, bioenergy, largely through Midwest agricultural activities. But a lot of these bioenergy products are consumed by coastal areas. Now you have tons of stakeholders involved from the environmental side and from the infrastructure side, of course, from the agriculture side. They need to be on the same page to figure out what is the cost benefit to all the parties involved, so that the production of the biomass in the Midwest could be beneficial to where the producers are, but also to those who are consuming the bioenergy products, largely is from the coastal areas. So in this example, we have publicly facing capabilities, engaging multi-sources of data, computational intensive models in the backend using high-end computing, but the stakeholders have no need to know this is happening in the background. They only need to focus on their pie charts, where are the facilities they need to locate for their energy distribution, and then give what if scenarios to this capability and figure out what will be the optimal solutions. So this is very collaborative, but leads to very computation data intensive workflows that should happen without getting those folks bothered for how this is happening. And there's extensive uncertainty involved between the answers and what's happening in the scientific methodology. So I hope to give you a few examples. You would have said, oh, this is not something I could do with my ArcGIS or QGIS. And that's the need to effectively create what I argue to be this transdisciplinary field, geospatial data science, that's galvanizing the intersection between geospatial science technology, cyber infrastructure computational science, and mathematical and statistical science. And in the center, of course, there are multiple elements, and there needs to be a curriculum to organize what would be the right elements to learn from each other, and also for training the future generation. But a lot of us in the geospatial domain might think, oh, I've been there before. What's different today? I've been dealing with geospatial data for ages. You're talking about geospatial data science to me. Well, I think a major difference today is scale. The problems, the scale, complexity of the problems, and also the computational scales involved to get us to the right insights and knowledge and answers for the questions we have to resolve. And of course, for spatial, if you're on the spatial side, you are familiar with dependence, uncertainty, heterogeneity, all these notions, right? If you're from the computational side, then you would appreciate the trade-off between performance, reliability, uncertainty versus validity, and of course, even the notions of complexity versus intensity. And this scale gets interpreted differently from the spatial to computational, but ultimately they need to be mingled together to form the core of geospatial data science. So let me give you examples of how this scale is manifested. So here's a study to extract hydrographic features out of the EFSTAR data in Alaska. So Alaska is one of those states actually not covered by the 3DAP program. So Alaska doesn't have the statewide LiDAR scan. USGS is supported. So we resorted to EFSTAR data. A little bit coarser resolution. But the methodology here is, again, to take into account multi-scale context. And This is a little bigger than Illinois County I showed you. Alaska is pretty big. Everything is relative here. So now if we look at this unit, spatial unit, watershed, and we want to extract hydrographic features out of this area, what we actually need to do is a multi-scale representation. We adopted a UNet model. For those of you who are not familiar with the UNet model, it's actually very powerful to represent contextual information. You know, for a big, let's say, image, you could have UNet to zoom in at different levels for these different layers, and then could go back from the fine resolution to coarse resolution. So it's pretty powerful to extract this multi-scale contextual information. That's exactly what we did, but with a geospatial focus. And the main methodology is published in this paper, but the study from the previous slide was application of this methodology. But the example I was trying to show here is we need to figure out how to represent multi-scale contexts in neural network models so that geospatial problems could be better solved. Now, I think a main point I want to get across here is why this is exciting as a scientific frontier. Well, overall, for geospatial science, a major excitement is because of the availability of geospatial data across scales, and because of the availability of tremendous computing capabilities and power, we are at the cusp of looking at big scale problems at fine resolution. So let's use Google Map or Earth as example. And oftentimes when you look at Google Map or Earth, you either look at a globe thing or a national thing, or you look at it and say, oh, where's Barami? What's happening local, right? You rarely look at both simultaneously. So Google's trickling you without giving you both at the same time. But scientifically, we're very interested in understanding what's happening at global large scales connected to what's happening at local scales. So with the availability of data and computation, we are getting pretty close. And for certain cases, we're there to bridge this gap. So this example of doing that. So you look at the entire US to understand the flood inundation levels, and you do this at fine spatial scales simultaneously. And this way, you would get the entire picture of flood inundation potential. And the methodology is pretty straightforward. You actually employ what this is referred to as HAND, height above nearest drainage network, which is pretty intuitive, meaning if there's a flood, let's say there's a river here, and I know the topography between the river there and me, and I know the distance, how I get there to the river. And then I could infer what's the flood potential from my location, right? You just calculate whether the water could move to here, and then the height. But the challenge is you have to do this across this big country at a fine scale. The good news is I talked to you about the topographic data, the elevation data. We're getting finer and finer resolution. We're talking about a petabyte scale for raw data, right? And for the river streams, there are about 3 million river gauges measuring the stream flows across the country. Any moment, water flows. USGS has those in partnership with different entities to get those measurements. Now, the question is, you got this flows information and you got this topographic information. How do you combine them both together across scale at fine resolution? That's, to me, a holy grail opportunity for geospatial science. There are many examples like this across social sciences and natural sciences with a geospatial focus. So we were quite excited by this problem. So this gentleman, David Mayman, who's a hydrologist plus GIS expert, he retired right before COVID from UT Austin. But before his retirement, I had the pleasure of working with him as a collaborative effort, solving that problem I described to you one slide before. And during this process, this is what he said. Combination of detailed GIS representation, such as topographic data, and also the river flow stream network, and this supercomputing approach we're taking, determine the flow, determine how the water is get to me from these river streams affecting flood inundation estimation. He said CyberGIS has delivered a major success for the nation. What he was referring to is later our methodology was adopted by NOAA for responding to multiple major flooding events. So this scientific methodology took us 2 to 3 years, about 20 plus people to develop on supercomputers, later actually adopted by agencies to respond to hurricane-caused floods. So with that, clearly I was telling you the transformative power of computing. The good news is rapid progress has been made and continue to be made, including the example of Aurora. Well, in the context of geospatial science and technology, we had this small-scale supercomputer called Roger, was developed around 2015 through NSF support, the Major Research Instrumentation Program. The idea at that time was, well, clearly the problems we were solving, such as the flood inundation, was data intensive as opposed to computing intensive, or you should say both, right? And a lot of times for us to study flood inundation, we actually look at maps interactively. It's not like you throw a job to a supercomputer, you go out to have coffee or meal, and then later you come back, you want to answer. That's not acceptable for geospatial scientists. So we want supercomputers to be more interactive. And of course, scalable, right? This is a multi-scale representation, as I was telling you, and integrated, meaning data handling and computation and this interactive interface for scientists to be able to do this work. So we assembled a single supercomputer that would allow us to do all this together. At that time was a crazy idea. That's why NSF funded us. It's what is called high risk, high reward. Okay, so, but if you look at today's mainstream supercomputers, it's all moving into this hybrid architecture, handling data, at the same time doing scalable computing, and then having cloud component making computing results much more interactively accessible. So geospatial computing does a little bit of moving the mainstream supercomputing to the way today we are pushing. It is real, so it is a single supercomputer based at the National Center for Supercomputing Applications. And now we virtualize this. It becomes a common infrastructure for our CyberGIS Center for Advanced Digital and Spatial Studies at Illinois and our collaborators. So with this advances in computing, let's talk a little bit about CyberGIS. And in fact, when I shared with you the concept of CyberGIS, this is sounding like cool, but around 2010, there was no existence of CyberGIS. It was a concept, right? So how do you establish actual software and hardware for CyberGIS? So thankfully, NSF funded this work to establish CyberGIS software with, again, a team science approach involving a set of academic institutions and Oak Ridge National Lab and Esri as industry partner and USGS. So the idea is to make CyberGIS software work. And before that, create what has to be CyberGIS software that is natively living this distributed high performance computing resources. Remember, for much of the history of GIS, GIS was living in our personal computing resources. And this is very different from physics, chemistry, and to some degree biology. So in those scientific communities, there are existing methods and scientific workflows. They were developed for a long time on high performance computing resources. And the CyberGIS was this more recent movement in geospatial science and technology and the related applications to move our community methodologies into directly harnessing high performance computing resources. Well, the good news is now we have a community platform integrating those different parts of CyberGIS software, including directly scalable codes and also Science Gateway. If you are familiar with what a Science Gateway is to give simple interface for the broader scientific community to work with high performance computing resources and their scientific workflows. And of course, middleware to help you organize the access to different high performance computing resources. So the platform here is accessible to all of you. We tried earlier today with your University of Wyoming credentials, you are able to register within a few clicks and automatically approved. If you're not convinced, talk to Shannon. And another thing that is powerful is this is the workflow developed for that collaboration. David Maidman and I, and among others, worked on for 2 to 3 years, mapping the national flood inundation. And this is a notebook that is on the CyberGIS X platform. Each and every one of you could go play with it. And you could walk through this notebook just like you would be one of our collaborators. So the scientific knowledge we produced through this collaboration for about 3 years is completely accessible for you to examine. And in fact, this notebook was developed for the purpose of communicating to NOAA, the National Water Center, National Weather Center, to tell them, this is how we did it. Go try it out. That's how we convinced them quickly they could adopt this methodology for their emergency response. And the technology for making this computational notebook to everyone here and beyond is what is referred to as CyberGIS Jupyter. So CyberGIS is the geospatial capabilities working with high-end computational data resources and the big data repositories. And Jupyter is the data science interface data scientists tend to work with. And the marriage here is to facilitate reproducible and scalable geospatial analytics. So if you want to know more details, check out this paper. But there's a challenge. Even though I mentioned each one of us here could work with this environment, but it's still a pretty high bar on the technical side. Even though you don't have to worry about how to work with big computers, but it's Python code, R code, and it's computer programs. So a lot of users are coming from the US, but the other continents are not as well represented. So to me, this is a digital divide, right? How do we democratize the access to such powerful capabilities and computational resources that continue to move so fast forward? But I'm thinking myself, perhaps on this side, these are my regular toys, including my group members. But I think some of you might be on this side. You still work with personal computers, QGIS, ArcGIS. So how do we bridge all this together, right? Have the entire ecosystem to address complex problem solving and to benefit the broad public. So this gets to the notion of data intensive geospatial understanding, because in the end of the day, it's not about these big machines. It's about what is the fundamental new knowledge and understanding we're able to grapple with together. And how do we foster a very open and productive ecosystem of knowledge production? So one of the things we did, and we continue to do, is this summer school approach. So we need to bring experts, grad students, junior scholars together to figure out what do we need to learn from each other to tackle these complex problems with computation data intensive approaches. So we had one 2019 at UIUC. Everyone was super productive and super happy as evidenced here. And we're doing another one this year. This is all NSF funded, thanks to NSF. This will be close to you folks in Boulder, Colorado. And this year's theme is convergence in action. So we have to work together. We must take actions with each other's input and contributions. So the iGuide Summer School is funded by this institute Jeff mentioned called iGuide, out of the NSF Harnessing the Data Revolution program. And NSF 2021 funded 5 national centers. iGuide was one of the 5. Now we've received $16 million for our first 5 years. And we have 11 institutions. Illinois is the lead one. I'm the PI, but there are 10 other organizations and institutions. And this is our URL. Hopefully it's easy to remember for you to get more information. We also are working with a variety of partners because the problems we're tackling, which I'll show you more, are really significant. Even if NSF would give us this much support, it's way less than what the solutions need for the complex problems we're addressing. So what are the complex problems we're addressing? Well, let's say our vision here for iGuide is digital discovery and innovation, computation data intensive approaches through harnessing the geospatial data revolution, the geospatial big data characteristics I was telling you about at the beginning. And we're aiming to transform geospatial and convergence science for holistic sustainability solutions. Why we think this mission is critical? Let's look at, for instance, the 17 Sustainable Development Goals from the United Nations. So if you want to tackle food security problems, you cannot ignore water security challenges, right? And a lot of times, the food production, water security challenges are tied to biodiversity challenges. And of course, all of these are somewhat related to climate change challenges. So all of these things are intertwined, and they are manifested across multiple geospatial scales. So this mission to look at these problems holistically, to come up with the solutions, I think is really, really significant as a scientific process and approach. So we have 6 key components of iGuide, and our taglines map, connect, and discover. You know, map, you could say it's geospatial science. Connect, you could say convergence science. Discover, that's what we do, scientists. Feel passionate every single day. And we're addressing a variety of sustainability challenges through convergence science approach, enabled by innovation of geospatial AI and data science, supported by advanced cyberinfrastructure. And we're running a variety of education workforce development programs, including the summer school as example, and we're engaging a variety of partners. We conduct evaluation of what we do, and also we pursue knowledge exchange transfer opportunities with our partners and with all of you for what you think could be cool for us to do. Our eyes and ears all open. So this is a quick summary slide to show you why we think this holistic approaches to sustainability challenges are so exciting and important. Let's say for the US, of course, the west side, especially California, got a lot of rain and snow, right, in the recent months. And of course, for the Midwest, sometimes we got too much rain. Also, sometimes we got too little. I think 2015 was a year we got a major drought that impacted crop production severely. That in turn impacted global food production through global trade. And since that point, Brazil became a much bigger supplier of soybean. And this became even more during the COVID years, and also impacted by the US trade policy. So now, because Brazil is pushing up the agricultural production, and that shrinks the land for nurturing biodiversity. So you would think what we're doing here in the US actually has direct implications on what's happening in Brazil with regard to biodiversity, right? And what we do here in the US is really multifaceted in terms of, let's say, water resources management. The US is facing a big problem in aging dams. We have, okay, I don't have that example. We have over 92,000 dams in the US. About over 60% of those are falling behind in terms of maintenance. So some of the dams we have are very risky if you consider some extreme events due to climate change. So how do we assess what's happening at a local and a regional level have this global impacts and repercussions? And are we ready to be able to assemble data and knowledge across these multi-scales to anticipate or even project and predict what could happen, not just contained locally and regionally, but across the globe? That's the scientific aspiration for IGUI. And in order to do this, you really need to bring a lot of elements together. Data, you will not need to be convinced at this point. We need a variety of data sources, but we also need domain knowledge, including domain models, to have data and models to work together. And we need to resolve these interactions at the specific geospatial scales and across scales, and also interdependencies across locations. And how do we translate such interactions into computational systems that might be somewhere else, not your local computers? So this notion of geospatial knowledge hypercube is a framework for connecting data models and computation together with explicit geospatial units and models and resolutions. So I was talking about the aging dams as an example, and the hypercube is a way of getting, in this case, text data organized into geospatial units. Text data, as we know, like from social media or literature, are very unstructured, right? They're not like traditional GIS data. You have raster vector, you could directly map them out. Text data, location entities are embedded in the text. It's supposed to be extracted with algorithms. So we're developing this hypercube, which I hope I could play this for you.
Have you ever wondered where are the locations our article talks about? Check out our Geospatial Knowledge Hypercube web application with a unique capability to combine text and geospatial data analytics. Let's take a news article as an example. So this paragraph talks about a dam failure incident, and there are lots of location mentions throughout. We copy-pasted this document into the system as an input and hit analyze. Just a second, then here comes to the recognized geographic entities. Leveraging a pre-trained language model on the backend, we extracted different types of geo-entities. Here, LOC for location in red, ORG for organization in blue, and there are also facilities abbreviated as FAC in green. I will further pinpoint them onto a map below. This combination between text and geospatial context enables a direct linkage between these two types of data modalities. So when we click on a recognized geoentity, taking this Midland Mall as an example, the map will be automatically zoomed into this place. And then when we click on the marker on the map, the text will also be filtered correspondingly to the only sentences where the location is mentioned. Here is another example for this Edenville Dam. So this text map linkage facilitates the user's interaction to quickly gain spatially explicit knowledge. And when we have a bunch of articles at scale, it will save a great amount of time and efforts for the users. In the current version, our application also supports exporting the extracted location entities with the geographic coordinates into a JSON file. Simply click this export button to do so. And the potential of this system is not limited to this demo. In the next step, we shall integrate other dimensions of the geospatial knowledge hypercube, such as the time and topic. That's the end of this demo. Thank you.
Thanks, John. That was John's voice, who's a postdoc I'm working with. I think Jeff's standing up. I need to wrap up this quickly, but we got a slow start. But anyway, so if you're familiar with GPT, the upper part is based on a similar model called BERT. That is a much simpler version of GPT. But I don't know how many of you worked with ChatGPT to do location analysis, but you don't go too far. This approach is to link that to geospatial representation and context to facilitate knowledge discovery, combining both. So, the idea is to really combine different sources of data and associated knowledge and models. And in order to do this, it's actually no existing yet any platform you could do. We had a simple demo, but the idea here is you have diverse data sources and you have community-specific cyber infrastructure capabilities. But these things are not talking to each other oftentimes. But a lot of times, convergent scientists, you and me, are not directly equipped to work with this many entities and capabilities. So iGuide, as a way to bring these capabilities together to form a single platform. This is still a prototype. I don't want to give you too much hope yet, but you could come here to work with some examples and data sources, and the Hypercube is one of the activities linking text data with other sources of data. So why we're doing this, my aspiration really is to make such wonderful, powerful capabilities widely accessible to a variety of science domains. And to me, this is super exciting, but also important. And of course, the world is only going to be accelerating in foundational advances in computing, and even quantum computing is not too much away from us. And this work is focused on solving a spatial optimization problem using quantum computing. So fasten your seatbelt. But at the same time, we need to recognize we have a lot more to do to democratize the access to these very powerful approaches, data and computation intensive. I know I'm running out of time, but this is very important because I think as we move very rapidly toward some very technologically exciting future, we at the same time need to be concerned about that.
When working in the geospatial data-intensive sciences, it's important to remember that the data we work with and the systems we develop are not just abstract concepts. They capture the real world and they affect real people. Geospatial data ethics is a field at the intersection of people, places, technology, and ethics. When you have an illness, should the government track your movements so they can notify the people around you who have gotten exposed? Should historical crime data be used to predict where future crimes might take place? Or would that reinforce existing biases in underprivileged neighborhoods? Hi, I'm Peter Darch from the Geospatial AI and Data Science iGuide team, and I study geospatial data ethics. High-level policy is important in establishing ethical principles, but it's the people who do the day-to-day work who make the small decisions that make all the difference. It's important to remember that everyone, at every stage of a project, takes actions that have ethical implications, Whether you are designing a research question, collecting, selecting, cleaning or sharing data, developing or testing software, or communicating your findings, you have an obligation to make sure that ethics don't get sidelined when you're working to deadlines and are under pressure to deliver. Think, how might these data or this tool be used in ways I don't expect and don't have control over? How might these data or findings be misinterpreted and used to harm others? It's a complex and challenging problem, but it's worth the effort to make the world a better place.
Thanks very much, Peter. Well said. I would not add too much given the time pressure here, but just quickly summarize. I think what I was hoping to get the message across here is we're facing this multi-tier knowledge domains, from the very top to the very bottom, that requires to be synthesized and integrated. And for a long time, geospatial science and technologies were just harnessing what's available to us. But now we need to open the box, and critical spatial thinking is vital from the top to the bottom, guiding the innovation, and recognize the power of digital transformation from the bottom to up. And we need to work tirelessly across these different knowledge tiers to achieve this integration and the synthesis that is so meaningful to science, but also to address real world problems. For iGuide, if you want to know a bit more, there's an article on Directions magazine describing our team and the problems we're trying to solve. And thank you for all the support, and especially NSF for iGuide. We cannot do anything without your generous support. And of course, I'm only one of the many members of iGuide to share what we do here today, and the credits go to all those amazing team members. Thank you. Sorry about compressing at the end. I realized I ran out of time, maybe lost some time at the beginning too.
Yes, yeah, and we did, and apologies for that. Thank you so much. This was really terrific. I don't know if there's a class in here. I know that some folks have 1 o'clock commitments, so feel free to get up and go. If they don't kick us out of this room, we'll take a few more minutes and have some time for questions if some folks want to hang around for a few minutes, and folks online might want to ask a question. So.
No,
class. All right. So we're going to have to wrap up. Thank you, folks online. Thank you, folks in the room. Thank you, Shaowen. Wonderful talk. Gave us a lot to think about. I can tell you already there'll be some follow-up to this and exploring ways that those of us at the University of Wyoming and our partners in the state will be able to connect to this. So this isn't the last time we'll be talking about this. So, all right. Please join me in thanking Shaowen once more.
Thank you all.